Hello students, welcome to part 3 of PYQ solution of the first chapter of class 12 AHS final year, electric charges and fields. Okay, so here we are going to solve previous year's questions of AHS final examination under Assam Higher Secondary Education Council. Okay, so link of the previous videos are given in the description box. If you haven't watched them yet, then go through. Okay, so before we start, please subscribe the channel, hit the thumbs up button, also share with your friends and inspire me to create new content for you. Okay, so if you want to follow me on Insta, this is my Insta ID. Let me write the ID here. Oza Lokhajit 123. This is the Insta ID. You can follow me on Insta if you want. Right, so now let's start. So this question was asked in 2013. So what is an electric dipole? Find the expression for the torque acting on an electric dipole placed in an external uniform electric field. Right, so first let me write the definition of electric dipole. What is an electric dipole? So electric dipole is nothing but a pair of equal and opposite charges. So is a pair of equal and opposite charges separated by a very small distance. So this is the definition of electric dipole. So now let's let's try to obtain the expression for the torque acting on an electric dipole, which is placed in an electric external electric field. Okay, so let me take a new slide. Okay, so now let me consider this is an uniform electric field, so that can be represented by parallel lines, right? So these are the field lines, uniform electric field. Okay, so this is the direction of the electric field, uniform electric field, and we have an electric dipole here, suppose. So this is an electric dipole, right? And this is positive charge here, and here it is negative charge, and separated by a distance twice a. This is the dipole length, twice a. Okay. Sorry, let me write it properly. Twice a. This is the length of the dipole, right? And it makes an angle theta with the electric field, and the direction of the dipole moment will be from the negative charge to positive charge. That should be the direction. This is the direction, as you can see in the blue color. This is the direction of the electric dipole moment P, right? So here you see this charge is positive Q, this charge is negative Q, and force acting on this charge is given by, we know that electric field E is given by F by Q, so F is equal to EQ, right, or QE. So if that is the case, then the force acting on this positive Q charge, that will be equal to Q into E, right? And this should be acting along the direction of the direction of the electric field, which is the positive charge. The force on positive charge should be in the direction of electric field, and the force on the negative charge, on this minus Q charge, this should be in the direction opposite to the electric field. So here also this is F is equal to minus QE, right? Minus QE. Okay, now you see here, you see this is positive charge, and force acting on this is in this direction, F is equal to QE, right? And this is negative charge, force acting on is in the opposite direction, which are equal. These forces are equal and opposite, so net force acting on the dipole is 0, but you see action of line at these 2 points are not in the same line, so that's why there will be a there is a couple of forces in opposite direction. Because of this coupling, so there will be a turning effect, right? So hope you have understood this. So let me write what I have considered here. I have considered a dipole which is placed in an uniform electric field. This is E, and the angle between the field and the dipole is theta. Here you can see. Okay, so now, here we have considered that this positive charge, this plus q charge, is at the point A, suppose. Okay, so let me draw the diagram clearly. Okay, just wait. Here this plus q charge is at the point A and the minus q charge is at the point B, right? So this is A, this point is A and this point is B, suppose, and force acting on this plus q charge is F is equal to Q into E, right? So just wait, let me write it properly. So this is the force F, right, acting in this direction. So now what we can do here, so let me draw a perpendicular from this point and this point as well. These two are perpendiculars. Okay, so if this angle is theta, then this angle must be also theta, corresponding angles, right? So this point is suppose C. Okay, so here we have considered this dipole where this plus and minus q charges are at A and B, right, separated by a distance twice A, okay. Separated by a small distance twice A, right, twice A, which is in an electric field and external uniform electric field E, right, electric field E as shown in the figure. So let me consider that P is the electric dipole moment of the dipole, of the electric dipole which is equal to Q into 2A, right, Q into twice A, right, and theta be the angle between vector P and E, right, and force acting on positive Q charge is F is equal to QE and force acting on minus Q is F is equal to minus Q into E, right? So net force, so therefore net force acting on you know, the dipole is equal to 0, right? That's what we can say. Now you see the forces acting on positive Q and negative Q are equal and opposite. Right, equal and opposite, but acting in different line, right? But acting in different line. Acting in different line. Right? Different line of actions. So the dipole tends to rotate. Rotate. In clockwise direction. Right? So now let me copy this figure and let me go to another slide. Let me take a new slide. Okay, so just here you see, let me go back to the previous slide. Take the screenshot of this. Okay, so here you see, so what will be the torque on this dipole? Now you see, suppose this is the dipole and both the charge, positive charge and negative charge, are experiencing equal and opposite force, right? Then you see the magnitude of each force and the perpendicular distance between these two forces gives you the torque, right? So that's why what we're gonna write here, the torque acting on the dipole, is tau, the symbol is tau not T, okay, is equal to force on each charge into perpendicular distance between the line of two force, perpendicular distance between the two forces, right? Perpendicular distance between the two forces. So now force acting on each charge, if you take the magnitude only, that is Q and E, right? Because of the opposite direction I have put here minus, right? But if you take the magnitude only, that is Q into E, so Q into E, right? And the distance between them, this is AC, this is AC, okay, this is AC. Let me mention one more thing, just wait here, that AC is perpendicular to BC. Let me mention that one also. So now you see, this is what we have got torque. Now if you see this triangle ABC, this is the dipole AB, right? Here is the BC and here is the perpendicular AC. Suppose here we have positive charge, here we have negative charge. This is A, this is B, and this is C, and this is the angle theta, right? So if this angle is theta, this must be also theta, because they are corresponding angle, right? So now you see, from this triangle, from triangle ABC, so let's find AC. So AC is perpendicular, and side opposite to the right angle is hypotenuse. Here AB is hypotenuse here. So sin theta, we know that perpendicular by hypotenuse, AC by AB, and AC is unknown to us, and AB is nothing but twice A. This is the length of the dipole, twice A. So that's why AC gonna be equal to 2A sin theta, right? 2A sin theta, right? So this is 1, suppose this is 2. So from 1 and 2, from 1 and 2, we're gonna have torque tau is equal to QE 2A sin theta. That's what we're gonna have, right? QE 2A sin theta. Now you see, torque Q into 2A E into sin theta. So Q into twice A, what is this? This is nothing but the dipole, right? P is equal to Q into twice A, right? So that's why what we can do, since the dipole moment P is nothing but Q into twice A, that's why we can write torque. So here we are taking the scalar form only, so then P E sin theta, right? P E sin theta. So if you write this in vector form, right? If you write this in vector form, now you see, we know that A cross B is A B sin theta n cap. N cap is the unit vector in the direction of A cross B, right? A cross B, which is perpendicular to both vector A and vector B, right? We know those things. I hope that you know these things, right? Now if you take the magnitude only, then we used to write this part only, that AB sin theta. So here we have PE sin theta. That's why we can consider that this is the magnitude of P cross E, right? We can consider this is the magnitude of P cross E. That's why in vector form, when you're gonna write in vector form, so in vector form, torque tau is equal to, we can write P cross E. We can write P cross E. So hope you have understood. So this is the vector form, and this is the scalar, right? So hope you have understood this. Now here we're gonna have two special cases. Let me go to a new slide. Here you see. So what is the magnitude of torque? Torque is equal to P E sin theta. We have got this, right? We have got this. So now special cases. Just wait, let me write this one here. So special cases. Number 1, or let me write A, when dipole is placed parallel to E, when the dipole is placed parallel to electric field, right? Electric field. That means theta is equal to 0 degree or 180 degree. Then what we will have? So this is the suppose electric field, direction of electric field, and the dipole is placed in this way. So in this way, then the dipole moment will be in this direction. So in this case, the theta is 0, or if you place in this way, then direction of the dipole moment is the opposite to the electric field. So then theta is 180. In this case, theta is 180, and in this case, theta is equal to 0 degree, right? In both cases, sine 0 and sine 180, sine 0 and sine 180, sine 0 degree is equal to sine 180 degree, both equal to 0, right? So for both theta is equal to 0, for theta is equal to 0 degree, we're gonna get torque is equal to 0, which is called stable equilibrium. Okay, this because here you see torque, here the magnitude of torque, that's gonna be PE sine 0. Sine 0 is 0, right? So that's gonna be 0. So this is the condition of stable equilibrium. Right, and for theta is equal to 180, the torque PE sine 180 is also 0, so that's why it's going to be 0. So this is called unstable equilibrium. Right, this is called unstable equilibrium. Right, in both cases, torque is minimum. Torque is minimum. Right. Now, what if theta is equal to 90 degree? Case B, when the dipole is kept or placed at right angle to E, that is theta is equal to 90 degree, and we know sine 90 is 1. So in that case, torque P is sine 90, that's gonna be P into E, which is the maximum. So I hope you have understood it, and thank you for watching. See you in the next video. Okay, stay connected. Do subscribe the channel, share with your friends, hit the thumbs up button, also hit the bell icon so that you get notified when new video will be uploaded. Right, so support me to grow my channel. Thank you.